equilibrium of a rigid body requires that the resultant force and the resultant moment acting on the body vanish. After resolving forces into x and y components, the conditions for equilibrium in a plane can be expressed in terms of three equations. 1. The summation of the forces in the x direction is equal to 0. 2. The summation of the forces in the y direction is equal to 0. And 3. A moment around any point in a body is equal to 0. For equilibrium in two directions, only three independent equations can be written. For an alternative set of equilibrium equations, one set of the force equations has been replaced by a moment equation. For example, the summation of forces in the x direction is equal to 0. We can then use two moment equations where A and B are any 2 points in the plane of the body, not on a line perpendicular to the x-axis. For equilibrium in two directions, only three independent equations can be written. In the third possible set of equilibrium equations, both force equations have been replaced by a moment equation, where A, B, and C are any 3 points in the plane of the body not on a straight line. An equilibrium problem can be simplified by selecting equations that result in only one unknown in each equation. Moment equations can frequently be used to eliminate unknowns by summing moments about the point of intersections of the lines of action of two unknown forces. What steps do we follow to solve any problem? The first step is to draw the free body diagram, converting every distributed load into a concentrated load, and find the x and y components for every force if the force is an inclined force. The second step is to start by writing your equilibrium equations, such as the summation of forces in the y direction equals 0, the summation of forces in the x direction equals 0, and the moment around any point is equal to 0. The last step is to solve for the unknown forces. Try to find the equation that leaves you with only one unknown first. Then you'll complete the other steps later. Let's look at an example. For the beam shown in Figure A, find the reactions at A and B. The first step is to draw the free body diagram. We convert every distributed load into a concentrated load and find the x and the y component for every force. So Fc here, which is the reaction in C, makes a 70-degree clockwise angle with the x-axis. We have the two components for that. We would say that the x component is going to be Fc times cosine 70, and the y component is going to be Fc times sine 70. The second step is to write your equilibrium equations. We have the summation of forces in the x direction is equal to 0. The only forces we have in the x direction here are Ax and 0.3420 Fc. In the y direction, we have the Ay, which is going to be positive because it is going upward, and the 2,400 and 1,800, which will be negative forces since they are going downward. Then we have the Fc of 0.9397. We also have the moment. In the problem shown, unknowns Ax and Ay can be eliminated if we sum moments with respect to A. With the moment A, we have only one unknown, which is Fc. If you solve for that equation, you will get a value of 1,660 pounds for Fc. Unknowns Ax and Fc can be eliminated if we sum the moments with respect to C. Any number of force and moment equations can be written, but only 3 can be independent. Each equation should be written to agree with your free body diagram. So if we take a moment around C and solve for Ay, we find our Ay to be 2,640 pounds. Then, if we yield back and substitute the value of Fc to be the summation of x forces, we get the value for Ax of 568 pounds. If we want to check that, we can put all of the numbers in the summation of y forces equal to 0 and confirm if the answer is correct or not. In another example, a force of 6,500 newtons is applied to the beam as shown in the figure. The uniform beam weighs 600 newtons. What are the reactions at A and B? Again, let's follow the steps of the summation of x forces and y forces, but before that, we have to show our free body diagram. We show the self-weight of the beam, which is 600 newtons, the external force of 6,500 newtons, and the reactions Ax, Ay, and Fb. Then we can take the moment around A. We know that we can isolate the Fb and not worry about Ax and Ay, because they are going to be omitted when we take the moment around A. From here, we can find Fb right away, and then if we take the moment around B, we will be able to isolate Ay and solve for that. Then you will have one unknown left, which is the Ax. We know that we do not have any forces in the x direction, so Ax is equal to 0. If you want to check that, you can put those figures in the summation y forces is equal to 0 equation. If the summation is equal to 0, it means you are on the correct path.